So in this lesson, I'm going to take the concept of oxidation and reduction, and I'm going to apply it to voltaic cells. Now, voltaic cells, in a voltaic cell, an oxidation and a reduction reaction occurs. And the cool thing about the voltaic cell is that because the oxidation and reduction reactions are separated, you can actually see the flow of electrons that can actually power a battery. So let's look at it. We're going to start on the left-hand side. What happens in a voltaic cell, you start off with a metal, a solid metal, for example, zinc. And so zinc is going to give up its electrons to become a zinc ion. Now, where those electrons go is that it's going to flow through that wire all the way over to the copper side. Now, really quickly, just to make sure we're clear, the zinc ions go into solution. Now, as those electrons hit copper, what happens is that the copper ions that are in solution, those are going to pick up those electrons to produce solid copper. So there's going to be more and more and more copper atoms being added to the copper bar that you see right there. So while you're losing zinc solid, you're gaining copper solid. Now, the reason why it's that way, we'll look at some values and some mathematics. But for right now, just accept that oxidation happens on the zinc side and for copper reduction, and we'll come back to it, I promise. Now, a couple of other pieces of information that I need to include. The first one is wherever oxidation occurs, that's called your anode, and the way that I remember it is because those are both vowels. Wherever reduction occurs, that's the cathode. So notice zinc is being oxidized, so that's the anode, and copper is being reduced, so that's the cathode. The other piece of information that I have not included is what exactly the salt bridge is. So if you look at what's happening, on the zinc side, on the anode side, you end up with more zinc ions in solution. So that ends up with a very positive charge on the anode side. While on the cathode side, you're losing copper ions, which means it's going to have a very, very low positive charge, if not a negative charge. We don't want that. The reactions that are occurring will not continue if you end up with a buildup of charge. So as a result, we have what's called a salt bridge. So that salt bridge provides ions in order to make sure that one side doesn't become too positive and one side too negative. So since there's a lot of zinc ions that are positively charged forming on the anode side, nitrate ions are actually going to be moving in order to balance that positive charge. On the other hand, the sodium ions are going to be moving to the cathode side to balance the fact that you're losing positively charged ions. So the whole point of this is just taking a concept we've already looked at, which is oxidation reduction, and actually being able to measure the flow of electrons. So let's look at this from a mathematical side. We're going to be talking about cell potential. So a cell potential is the potential difference between the two electrodes of a voltaic cell. And so a cell potential is responsible for why those electrons will spontaneously move from the zinc anode to the copper cathode. Think of it like a waterfall. You never question why water moves from the top of a waterfall to the bottom. It's simple gravity. Well, the cell potential is the same concept. The reason why those electrons move is because of that difference in potential. Think of it, if you have a hard time picturing that, just think about the waterfall example, and just think at a higher point, water's going to go from a high point down to a lower point. Now, another term for cell potential is the electromotive force, the force that's forcing those electrons to move, and we call that EMF. Think of it just like gravity in the waterfall example. Now, cell potential is labeled as E cell, and if you're at standard conditions, meaning you're at 25 degrees Celsius, then you have that naught symbol right there. And the units for your cell potential are going to be volts. Now, volts is simply joules, which is a measure of energy, a unit for energy per coulomb, which is the charge. So a volt is a joule per coulomb. So we're going to be using the units volts. So let's actually put some math to this to understand why the electrons move from the zinc side all the way over to the copper side. So you have half cell potentials, which are given to you. And so half meaning you're either looking at reduction or oxidation, but the potentials that you're given are actually only the reduction potentials. And so as a result, if you have a substance that is oxidized, you need to take the negative of the reduction potential. Now here's the key part. When a reaction is spontaneous, the net cell potential will be a positive value. Okay? The more positive the cell potential, the more likely that reaction is going to occur. So for example, I automatically know because zinc is oxidized, I know that the cell potential for zinc's oxidation is going to be more positive than copper's cell potential for oxidation. In contrast, because copper is reduced, I know its cell potential for reduction is going to be more positive than zinc's cell potential for reduction. So the more positive it is, whichever element has a cell potential that is more positive for either reduction or oxidation, that is the one that's actually going to occur. All right, so we're going to do more math and we're going to work more with cell potentials in the next section. This was just to introduce you to the mathematical side of it, but let's look at one example before we finish. If you have a galvanic cell that has silver and tin, which is going to be reduced and which one's going to be oxidized? So let's take the example of zinc and copper, but change the elements. Well, I need to determine the cell potentials for silver and for tin. So I know that the cell potential of silver is positive 0.799 volts, all right? I know that the cell potential of tin is going to be negative 0.136 volts. Now this is for reduction because I'm always given the cell potentials for reduction, the reduction potentials. So what that tells me is that silver, because it's more positive, is going to be reduced. That also tells me, because if you want to find the cell potential for oxidation, the oxidation potential, you simply need to take the negative. Well, if you take the negative of those two values, then tin is going to be more positive than silver. So that tells me that tin is going to be oxidized, while silver is going to be reduced. So that's how you take quantitative data and are able to predict what's going to be oxidized, what's going to be reduced. And with this information, you can create your own voltaic cell.